So, as we've seen in other topics in this course, differential equations will be approached in an analytic approach, a graphical approach, and a numerical approach. We just did the analytic approach. That was the separation of variables and anti-differentiation. So this video is going to be talking about slope fields, which is the graphical approach to differential equations. What we're going to try to do is turn our differential equation into some sort of graph. It's called a slope field, and the way that works is we're going to determine the slope of each solution curve at every single point. So how does that work in practice? Well, we can't literally find every single slope, but we can find many slopes and find a pattern. So I'm going to return to our differential equation that we saw in the analytic approach, the one that we spent some time on. It was dy dx equals negative x over y. We already solved that one analytically. Now I'm going to try to graph this differential equation. So the question is, which points do I pick? Well, I pick all of them. So I'm going to start with, maybe I'll start with the point 0, 1. X equals 0, y equals 1. So dy dx is the slope of the solution curve at every point. So in this particular case, x equals 0, y equals 1, we'll get negative 0 over 1, which is going to equal 0. Okay, so what that tells us is that if we have a solution curve that goes through the point 0, 1, then the slope of that solution curve is going to be 0, which is a horizontal line. So I'll write a small tangent line right there. We don't know where the curve is right now. That's not very nice. Let's try that again. And we don't know where the curve is, where it's going, but we know that it's horizontal at that point. And you might think about other points, for example, 0, 2, and 0, 3, and 0, 4, and 0, anything. Those are all going to have the same horizontal slope. So I'm not going to draw a very long horizontal line because if we think about tangent lines, we realize that they're local linear approximations. So our curve only looks like this in that general region. We can also look at negative y values. 0 divided by negative 1 is still 0, and 0 divided by negative 2 is 0, and etc. Notice I'm leaving out 0, 0. That's kind of a special point because 0 divided by 0 doesn't necessarily equal 0. It could equal other things, as we've seen in the past. So I just won't put anything at 0, 0. Okay. Let's consider another point, 1, 0. Well, that's going to put the negative 1 over 0 as our slope. Now that's undefined, but it's not ungraphable. It means that our rise is negative 1 while we run nothing at all. So at the point 1, 0, we're going to have a vertical line. And likewise, you can imagine that every other point, 2, 0, and 3, 0, and 4, 0, and anything, 0, is still going to be undefined. So that means that all of these points, 2, 0, 3, 0, 4, 0, and off to the left at negative 1, 0, all of these points are going to have vertical tangent lines. So let's find some maybe more interesting points, like maybe where we don't have 0 as one of the coordinates, like maybe 1, 1. Well, 1, 1, x equals 1, y equals 1, we have negative 1 over 1. That's negative 1. So at 1, 1, this point right here, our slope is negative 1. So we're going to have kind of a line going in this direction. But I don't want to connect it all the way from this x-axis to this y-axis. Again, this is a local linear approximation. And we can try 2, 2, and we'll see that that's going to give us the same negative 1 value. In fact, anytime x equals y, think about that. If x equals y, then we're going to get negative 1 for our slope. So every single point on the line x equals y, or y equals x, that will have a slope of negative 1. And we can keep on doing this for all the points on the plane. Another nice one to try is maybe 1 comma negative 1. So that's going to give us a negative. The x value is positive 1 and the y value is negative 1. So the double negative gives us positive. So 1 comma negative 1 gives us, at this point right here, a slope of 1. So I'll maybe do a little line like that. But of course, anytime x equals negative y, then we're going to get, in this fraction right here, we're going to get the same answer, right? We're going to get positive 1 for our slope. So as long as we're on the line y equals negative x, we're going to have that slope of positive 1. And we could do this all day long, right? It takes a long time to fill in the coordinate plane. So in practice, we're really not going to do so many of these by hand. We're going to probably do no more than, say, 9 of these on a particular graph, and from there we're going to call it a day. But you can kind of start getting the sense as to what a slope field looks like. In practice, if we want to see a big slope field, either it'll be given to us or we'll generate it with a computer. And we'll show you how that works in just a minute. But before we do that, let's take a look at, maybe you can see a shape in here emerging. And if you don't see the shape, then remember the general solution we had, x squared plus y squared equals c. And in fact, one of our particular solutions was x squared plus y squared equals 25. I hope you recognize these as the equations of circles whose center is at the origin. And you can imagine lots of different circles centered at the origin, and each one of these little tangent line segments would be tangent to one of those circles. Okay, so so we can see what that looks like. Here are some instructions on how you can graph a differential equation in a TI-Nspire. I'm not going to spend time in this video going through that. You can find a video online that will explain that. But the result should look something like this. Okay, so you can see that this is a much more detailed slope field than what I was doing by hand. And that's what technology is good for. It's good for doing things that we don't want to do by hand. We would never want to graph this by hand, but now that we have it, we can look at it, we can definitely see those solution curves in the shapes of circles centered at the origin. Cool. So how do we use the slope field? Well, we use it to kind of approximate particular solutions. This is the general solution. This is the entire slope field is the general solution to the differential equation. But if I give you an initial condition like 1 comma 1, then that should give us a seed value for getting that solution curve. We know that 1 comma 1 is a point on our particular solution. Okay, so let me zoom in on this. And we'll take a look at this point right here, the slope is equal to -1. That was one of the points I picked earlier. But as I move away from that and get closer to the y-axis, our slope gets less steep. And in fact, it horizontalizes, if that's a word, once we get to the y-axis. And as we pass the y-axis, we start going towards the x-axis again. We start curving down. And it shouldn't be surprising that we're kind of tracing out a circle. Okay, so we're kind of letting those tangent lines, those little bitty tangent segments, guide us towards the direction. Remember that if we're close to one of these line segments, it should be a tangent line. It should be going in the same direction as our curve. So I'm never going to see something like this on a solution curve because those are not tangents, right? So, so follow the curve. So with that particular solution, you might ask, should we graph the bottom half of the circle as well? And the answer is you could. It depends on the problem, I guess. Sometimes it might say graph the solution curve where you've got x squared plus y squared equals, I guess in this case, 2. And if you graphed that entire curve, yeah, you would have the bottom half of the circle. But if it said that the particular solution was y equals a function of x, then don't graph the bottom half of the circle because then you're not going to have a function anymore. So it's not a huge point of contention, but you have to decide what makes the sense in the problem that you're working on. So anyway, if we draw another solution curve, I think the next one gives us another point, if we can find it, of -2, 3. So -2, 3 in a different color. -2, +3 is up here. And we can kind of follow those tangent line curves. It's getting more and more vertical, and it's going to drop down to somewhere right here. And of course, we know that this is going to be a semicircle, so it's going to look something like this. And maybe that's what it would look like, something along those lines. That's not perfect, but it's the right basic shape. And then the last solution curve, I'll circle that in red. And then the last solution curve we have is 2, -3, and you might have a sense as to what is about to happen. But if we take a look at 2, -3, which is right down here, we're now in the bottom half. So we're going to do a semicircle down at the bottom. And it might not be surprising at all that these two guys meet up at the same place, because 2, -3 and -2, +3 are equidistant to the origin. So they're on the same circle. I'm doing my best to draw a nice circle, but my drawing pad is not allowing me to. There we go. That's good enough. So the red would be the solution curve that goes through the point -2, +3, and the green would be the solution curve that goes through the point +2, -3, and they are the same circle. There's just the bottom half and the top half.